All right, today we're going to talk about displacement and velocity. Okay, so when you are describing an object's motion, you have to use a frame of reference, okay, which is a concept that you may be familiar with and you may not. Okay, some frames of reference are more useful than others, depending on what objects you're looking at. Okay, and in physics, you need to keep your frame of reference constant for the entire working of a problem. So you can't be looking at one thing to determine motion and then change what you're looking at later on in the problem. It's got to stay constant. Sorry, don't mean to move on without you. So here's an example for you, right? If we're looking at a train and we're trying to decide if that train is moving or not, we can't look at just the train, right? We have to look at the background that the train is on in order to determine if it's moving. But there are several background systems in which the train is technically moving, right? For example, if you look at the stations that are along the path of the train and you compare its position to those, then you can see that the train is in fact moving, right? It went from one station to the next, therefore it must have moved. However, you could also compare it to the Earth, right? Where it is on the surface of the Earth changes. Also, the Earth is spinning, so even when the train is stationary, technically moving when compared to the rotation of the Earth, right? You could also compare it to the solar system, because the Earth is moving around the sun, and our solar system is orbiting other solar systems out in the galaxy, right? So compared to that, everything is always moving all the time. So you can see how some frames of motion are more useful, right? When it comes to the train problem, if we're trying to decide if the train is moving, in terms of usefulness for us, probably the surface of the Earth or the train stations are the most useful, right? Because if we compared it to the solar system and use the solar system as our frame of reference, the train is always moving. The train is never not moving. And that doesn't really help us solve our problem here on Earth. So we need to pick one frame of reference, find a useful one, and make it consistent, right? We can't, in the first half of our problem, discuss the train's movement compared to the train stations, and in the second half compared to the solar system, because that's going to cause problems. Your frame of reference needs to be consistent throughout the whole problem. Oh yeah. So, like I said, only some are useful. Pick one, stick to it. So now that we've talked about how we can tell if an object is moving, we're going to discuss a little bit about measuring that movement. And the first way that we measure movement is using displacement, okay? The length that a straight line drawn from an object's initial position to its final position is your displacement. Okay, so where you started to where you ended, shortest possible line in that direction. So if I start here and I walk all the way around the classroom, but I come back to the same position where I began, the shortest line from where I started to where I ended is a dot. So my displacement would be 0. Whereas if I walk this direction to the front of the room, now I'm probably 8 meters east of where I started. So that would be my displacement, 8 meters to the east. Okay. So shortest possible line in the direction of movement. Okay. Your formula is going to be change in position, x meaning the initial coordinates of your object. So your final position minus your initial position is going to give you your displacement. And displacement needs to include a direction. So, displacement does not always equal distance. And your displacement can be either positive or negative, okay? When I walked all the way around the classroom before and I ended where I started, my displacement was 0, but my distance would have been the sum of the lengths of all of the paths that I traveled. So if you go forward and then come back some, your distance and your displacement are not going to match up. They're not always the same. In physics, in general, we say that moving to the right, the east, or moving up or to the north are generally considered positive directions. And the opposite of those, moving to the left or to the west or down or to the south, would be considered negative directions. So if I moved 30 meters north, we would say my displacement was 30 meters north, and it would be a positive displacement. Whereas if I moved 30 meters south, we would say negative 30 meters. Okay, so it's another way to indicate, instead of having to use the cardinal directions or having to say right or left, they will indicate it with positives and negatives instead. Let's talk some velocity now. For a complete picture of an object's motion, you need more than just their displacement. You need to know more than just where did they move to. You also need to know how quickly did they move there. So the speed of your object needs to be factored in. And when we start factoring in both a direction and a speed, we get velocity. Okay? Average velocity is equal to the change in position of an object divided by the change in time, which could also be said as the displacement divided by the time interval. So, if you're solving for velocity, you're using displacement divided by time. And here's your formula if you want to write it out longhand. Velocity average is equal to the change in position divided by the change in time, which could also be written as x final minus x initial divided by time final minus time initial. You do not need to feel like you need to write that whole equation out. It's written in words. You don't have to use all the symbols, but I just wanted you to see it there so you were familiar with it. It's important to remember that speed and velocity are not the same thing. Okay? Speed doesn't include a direction. Okay? Average speed is equal to your total distance divided by your time. So not your displacement, not the shortest distance possible, but in fact your total distance traveled, the length of all of the paths you traveled would be summed up for your distance divided by your time. So you're not going to get a direction. It's going to be different. Pause there for a second. Okay, so you can view velocity nicely on a graph, okay, if you make your x-axis time and your y-axis distance, okay? Then if you plot it that way, the slope of the line is going to be equal to the velocity of the object. So slope is rise over run, right? So distance over time, you're going to come up with the same equation. So if you take a look at this, you can go ahead and draw a graph on your chart there. You can see we have time on the x-axis in seconds, and we have position or your displacement in meters on the side. So we can solve for the slope of this line. So they traveled, let's see, looks like about 8 meters in 8 seconds. So their velocity would be 1 meter per second. That's the slope of your line there, okay? And the nice thing about this is if we are drawing a line like this, you can include a negative displacement, right? And still get yourself a line to go off of. So when the velocity is constant, we get this nice straight line. But how often do you have a constant velocity?
It's not the same.
Are you going real into detail with your graph? That's pretty good.
Yeah.
Then it's
Well, I mean, there's another example coming up, right? So here's a nice distance time graph for you. You'll notice that your speed isn't always going to be constant. So if you take a look at this curved line here, the one that's in green, you can see that if you are charting a velocity that's changing over time, that's speeding up like this, you're going to wind up with a curve as opposed to a straight line.
So like a ball going downhill and slowly picks up speed.
Right, yep. And if you were charting an object that slowed down, the curve would go in the opposite direction. So it would start really steep and go gradually into a curve that would like flatten out towards the top of the graph. Okay? So that curved line is increased speed over time, and your instantaneous velocity is your velocity at an exact moment in time, which normally we don't measure. Like your speedometer shows you your instantaneous velocity, right? It tells you exactly how fast you're going right now, and if you change, the speedometer changes with you. On a graph like this, any one point, like set of XY coordinates, would be your instantaneous velocity along that line. And the nice thing on a curving graph like that is if you draw a line on it that's tangent to that point on the line, then you're going to find the slope of that line and get your instantaneous velocity at that moment, which is kind of nice. So I'll come back to this slide, but I'm going to take you back one slide just for a second so we can look at what that looks like, right? If I put a point on this line right here, and then I draw my line that's tangent to that, and I find the slope of that line, that will tell me the instantaneous speed at that specific point. So. Because your speed is never quite constant, right? When you're traveling, you speed up, you slow down, sometimes you stop. So you're going to wind up with different speeds. All right, that is what I have for you today.